Okay, good morning, guys. Today we will continue with the rest of the chapter called Analysis of Algorithms and Trees. As you see, this is divided into two parts. In the first part, we are discussing the methods, how we can evaluate the performance of algorithms. And in the second part of this chapter, we will discuss the fundamentals of trees, tree data structures, and these are quite important, especially in computational geometry, in computative design. We make use of such special data structures a lot, and you have also experienced kind of a tree in your first mini project. I hope you enjoyed it and have accomplished the given task. And as I said, I will be discussing some issues about the first mini project, and I will introduce you the second one at the beginning of our next lecture in 1 hour. I will quickly review the first part since we did discuss the first, I think, about 20 slides on last Thursday. I will go through it and then continue with the remaining slides. We said that there are some programs which are written to implement a given algorithm. An algorithm is a kind of a set of instructions given by step. With the help of it, we can solve various problems. And in implementation, we can use any programming language, any type of computer. So these are called as simple programs or scripts. And the thing is that we can implement these algorithms by using various languages, various computers, but we cannot easily measure the performance of these implementations. We should be actually measuring the performance of algorithms, since the rest is kind of an implementation and it depends on the experience of the user. It depends on the computation power of the computer. So it's quite subjective. So it's better we only focus on the algorithm, and we will discuss mainly a method to compare the performance of the algorithms. And we said that there might be similar different implementations, but executing the same algorithm, if you remember, these are exactly the same, summing the numbers up to n. And we said that we need to find actually kind of a way which is independent of the capability of your computers, independent of the programming languages. And we have discussed we performed a kind of a benchmark analysis. This was our function for the summation of numbers up to n. We did it for 5 times. We tried to sum the numbers up to 20,000. And as you see, it's almost the same. But if you increase the number, you'll obviously see that the time spent is also increased. As you see, the given number is increased by 10, and the computational time is almost increased by 10. So we have a kind of a linear relationship. But if you have a simple equation, simple expression instead of a for loop here, in the previous definition we had a for loop, but right now we have a single expression. So it shouldn't be depending on the number of inputs. So now let's have a look at this list. We have different inputs starting from 20,000 going to 200 millions. So this is a huge difference. And as you see that in the computation time, we don't have any difference. They are almost the same. We have little difference. And we said that this is mainly due to the operating system, let's say some task. It may have some interrupts, doing some various scripts, running various statements. So that's why we have little difference between the times. Obviously, we said that if you have iterations in your algorithms, you need to do more computation. And in the previous implementation, we said that there is a linear relationship between the number of inputs and the computation time. And it's quite difficult actually to compare these implementations if you just measure the time. And we said that instead of time measurement, instead of performing benchmark analysis, we need to have a kind of an independent method. And this independent method is called as big O notation. And we will be using the actually basic unit of computation. This will be usually equal to the given number of inputs. And what we are going to do in this method, we will actually count the number of expressions, the number of expressions performed per number of units. And we will have such an expression at the beginning of this analysis. This is actually representing the total number of expressions in the given implementation. In the summation example, if your number is, let's say, n is equal to 5, then that means you're going to run your for loop for 5 times. So that's why we have n here, and we have one extra statement for the initialization. So this sums up actually to 1 plus n, and it's equal to the total number of statements. And we know that n is this is equal to the size of the problem. Our time will increase as you increase the value of n. And we said that we will always consider the expression, consider the term with the highest order. And if you look at this expression, we have the order of n greater. The highest order is here 1. And this is 1 times n to the 0, and this is n 1 times n to the 1. So our highest power is 1, so that's why we will say that this is a linear time complexity. But if you have a higher power, we will assume that as the number of inputs gets larger, then this dominant term will be overpower the rest. So that's why we will only keep it and ignore the rest of the terms. And this is called as big O notation, and we will be using such an expression of f of n. Now we will see an example here. This was our t of n, and we can say that O of n is equal to the term with the highest power. So that's why it's equal to O of n. And if you look at another example, we have 5n squared plus 27n and plus 1005. So this is our highest power. That's why this will be the f of n. So we will say that this has a quadratic time complexity. And in some specific cases, it will be quite difficult to actually have such a t of n expression. In such cases, we will try to find the best solution, the worst, and the average solution, and try to comment on these cases. And we get gone through these functions. I don't want to spend time once again on them, but these are the popular actually functions we're going to use in this analysis of algorithms. And we were discussing some types of time complexities. We said that if you have a single expression, if your, let's say, algorithm does not depend on the number of inputs, then you can say that your algorithm, your implementation is constant in time. Regardless of your size of input, whether it's very small or large number of inputs, it doesn't matter. It will always take the same amount of time. In logarithmic cases, in logarithmic time complexity, our actually computation time is increasing as a logarithmic function. And the most popular example is binary search. We had an example about it. And then we have a linear relationship. It's not that difficult. In the summation example, once you use a for loop, then if you have a single for loop, then it will be a linear time complexity. The thing is that your for loop should depend on the number of inputs. If it doesn't depend on the number of inputs, then you can maybe say that it's constant in time. So this is a must for the linear case. For the linear arithmetic case, it's a multiplication of these two, and we have a specific algorithm, merge and sort. In a moment, we will discuss this example, linear arithmetic time complexity. Now let's focus on the binary search once again. So please stop me if you have questions about it. In this case, actually in binary search, what we do, we have initially a sorted list. As you see, there is in the first row, we have the values starting from 6, ending with 97. And as you see, we have 15 integer values. This is the first value, and its index is 0. And the last one, its index is 14. Now the question is, can you find 33 in this given list? And we know that this is an ordered list, so we should find a better way. Instead of checking each number one by one, we should find a better way, and it should be, let's say, its time complexity should be less than linear. Since in the brute force method, what you're gonna do, you will have a for loop. You will always check each item one by one, and then once you find the given value, you will stop and comment that it's in the list, and you are done with that. But this is linear time complexity, and since it's a sorted list, we should have a better way for the computation for this search problem. So what they're going to do, we will simply divide this given range into halves. And then depending on the given value, we will whether continue dividing into halves or stop if you find that your item is at the middle of your, let's say, new range. So this is how we start. We have the lower ends, higher end, and the middle numbers. And then what we do, we check whether our given number is on the left-hand side or right-hand side, and obviously 33 is on the left-hand side. So we continue dividing it into two halves, lower, middle, and higher. I can see that now my number is on the right-hand side, so I will keep this part and have another middle, lower, and higher items. And the thing is that the middle is actually belonging to the lower end side, so it's somehow part of the left-hand side. And then what we do again, we check that our number is this time on the left-hand side, so we need to keep it. And I know that the next number is actually number after the lower item, so we don't need to keep the middle value. We will only keep the fourth item, so it's 33. And now we will check and see that this lower value is equal to the higher value. And at that point, we should stop searching and comment that this given value is in the list and its index is 4. And we said that the time complexity of this implementation, this approach is logarithmic, since we are always dividing the range into two halves and decreasing the size of our problem continuously. So initially, the size was 15, and at this point, the size is 7, now 3, and at the end, the size is equal to 1. So this is how the size of your problem decreases, and that's why we can call it as an logarithmic time complexity. Any questions, guys? Okay. This is the implementation. We have some initialization steps, and then we are checking whether the given first value is less than or equal to the last, and we didn't still find the value. And then, as you see, we continue dividing in our, try to find our midpoint by dividing the range into 2, and then check whether our given value is the midpoint or not. If it's the midpoint, then we can stop this search. But if it's not midpoint, then we need to do some arrangements, find the new higher point or the last point, and find the lower point or the first point. So we continue the search until we come up with the item, or if the item is not there, then we can finish this job actually once you cannot divide this range anymore. So we have another specific algorithm. This has a linear arithmetic time complexity, and this is called as merge and sort, and sometimes we call it as a kind of a divide and conquer algorithm. So we are dividing the ranges into, once again, halves, and then we do some tasks on these halves, and then later what we do, we combine these halves one by one again. So this is kind of merge and sort algorithm. So let's have a look at this example. As I mentioned, we will be dividing the given array, given set of, let's say, I don't know, integers, doubles, or strings into two halves. Then we will do some operation on these halves and merge them together later after these operations are completed. And the operation in this problem is sorting, but it can be anything. It doesn't have to be just a sorting operation. But the thing is that we will not be actually doing this sorting once you have the two large halves. So you should continue dividing these into very small parts and then start actually joining them, doing the sorting operation and then joining them. We will have a look at an example in a moment. By such an approach, you guarantee that you have an n times logarithm of n time complexity. So this actually comes from, we are performing a kind of a search operation. So we are dividing it into halves. So that's why we have this logarithmic term. And since we are doing for n times, we are dividing it we are actually sorting the arrays for n times. So that's why we multiply it with the logarithm of n. So now what we are going to do, this is our actually kind of array. And as you see, we have smaller numbers, higher numbers, some mid values. And at the end of this problem, we want to have a sorted list. So the problem is sort the given array in an increasing manner. So what we are going to do, we will divide it into halves and then work on these halves or little, let's say, some portions. So assume that this is our first sub array, and at this point, as you see, we stop. I think we have how many? 4, 8, I think 13, and if I'm not mistaken, there are 13 items. And this is our actually initial, let's say, parameter. It's up to you. You may decrease it maybe to 4, to 3. It's up to you. No matter, the time complexity will always be the same. So what we do, we divide our whole range into such sub-arrays. Once you have these sub-arrays, what you do the ordering. So this is a sorted sub-array. And we do it for the second one. And then later what we do a merge operation. The third sub-array, fourth sub-array, we sort them separately and then merge them. And then later what we are going to do, we will merge these two a bit larger sub-arrays. So this one is this is actually the first half. It's now sorted. And then what we do the same operations for the second half. So this is another sub-arrays. They are sorted separately, merged together, sorted separately, merged together. Again, we have the second half. This is sorted once again. And lastly, we need to join these. We need to merge these halves together and have the final result. And as you see, this is a sorted array. So there's a question, what determines the length of the smallest subarray? It's up to you. We don't have a specific definition, but you may keep it to 1, for instance, or 2. 2 is better. since you cannot sort it if you have just one item in your subarray. So the minimum value is minimum value is 2. So once you order these 2 values from small to larger one, then you can do it for all little arrays and then merge them once again, sort it and do it for many times and have the final result. Any questions, guys, about this linear arithmetic time complexity? Questions? Okay. We have some more actually time complexities, but they're not that difficult. This one, the first one here on this table, is called as quadratic time complexity. I have already mentioned about it at the beginning. Once you have, let's say, 2 for loops and 2 nested for loops, and if they depend on the size of your inputs, if they all depend n here, then we can say that the order of growth is n squared and it has an quadratic time complexity. So what is done here with the help of these 2 nested loops, they are checking all the pairs of a given array, let's say, if the summation of these pairs is equal to 0. If that's it, then we have a single expression here. We have a counter and we are increasing the value of the counter. Then we have a similar version. This time the order is 3. It's a cubic time complexity. We need to have a triple nested loop. And here you see the size of the loops is depending on the given value n. So what we are doing here, we are again checking these triples, checking the summation of these triples, whether it's equal to 0 or not. Once it's 0, again, we increase the counter as we have done in the quadratic case. And then lastly, we have an exponential time complexity, but that's a very rare approach, and we don't want to have such a time complexity since, as you see, by such an order 2 to the power of n, if your given input is too large, then this will go to the infinity, maybe in a little number of inputs. So we don't prefer to have such implementations, such algorithms, and this is called as excessive search. And for instance, we have an example. If you have a large set of numbers, if you check all the subsets, some details about it, then that will be an exhaustive search, and its time complexity is exponential. So there's a question: if you have break-in inner loop of 2 nested loop, will be order growth as same as 2 nested loop n squared? As far as I got your question, I think you say that you have a kind of an break here. So it depends. If you have that break for all the time, then you may decrease the complexity, but probably your break will depend on some values. And since in this time complexity evaluation, we are always considering the worst case. So if in the worst case, in the worst scenario, if your break doesn't actually happen, so we can say that this is still quadratic time complexity. But if you can somehow prove that, we will not be going to the end of the second loop, then you may comment that it's not quadratic, depending on what you are doing here. If you do a kind of a binary search, you may say that it is linear arithmetic, log linear, as we have seen in the merge and sort algorithm. So it depends on whether you are breaking all the time or you break sometimes, depending on the specific condition. And we should always consider the worst case. Any other questions, guys? So this is an illustration, a kind of a graph showing the size of our problem with respect to the time versus problem size. So as the problem size increases, as you see, their computational time increases. Let's have a look at the first one, the constant one. Since the number of operations we are performing in the constant time algorithms is not changing, so that's why it's always the same. Whether you have 500,000 inputs or just a single input, it doesn't matter. It will always have the same computational time. If you look at the logarithmic case, it's one of the best actually type of implementations, type of algorithms. It's not increasing too much. It's increasing, but not as high as you see as the linear one or the quadratic one. The linear one is an obvious one. As we increase the size of the problem, the time spent will increase linearly. And we have a very close one, the linearitmic one. You can remember that merge sort algorithm was an example to linearitmic time complexity. So they have kind of very close time complexities. But on the left-hand side, as you see, these are the actual type of algorithms we don't want to have in our problems. The thing is that if you increase the size of the problem, the time spent is actually increasing a very short amount of time, or once you increase the size of the problem, even very little. So that's why in our solutions, we should always try to use maybe logarithmic algorithms or linearitmic or linear ones, but try not to use, please, quadratic, cubic, or exponential algorithms. This is a better view. I think this is a logarithmic plot. You can now much see the difference, easily see the difference between the exponential, cubic, and quadratic. In the previous one, it's quite difficult to see the gap, but here is much easier, and you can see a more gap between the constant and the logarithmic, and also more gap between the linearitmic and linear. So this is actually summarizing the time complexities of algorithms. So it's better you always use kind of algorithms in this range on the left-hand side, not the ones on this upper range. Any questions? So let's have such an example. We have kind of some assignments here, A, B, C, and then we do some operations, some another operation. So what is T of n? Can anyone tell me the T of n of this, let's say, implementation? I'm asking T of n, not O of n. We should first find T of n and then find O of n. So what's it? How we do the actual computation? So here we have three expressions. Since this will not depend on the number of inputs, it's independent of the given inputs. And then what we have here, we have a nested loop, 2 for loops, and they all depend on the number of inputs. And we have some kind of multiplications here. So I can say that this is n squared. And then at the next for loop, we have again a loop depending on the size of the problem. The size of the problem is n, and we don't have another important operations here. So we can say that we have another term as n. And lastly, we have an assignment here, d is equal to 33, and this is independent of the size of the problem. So I can say that this is T of n. And then what is O of n? the highest order is here. This term has the highest order, so I can say that it has an ON square time complexity, or we can say that this is quadratic in time. Any questions, guys, on this simple example?
Hocam ben bir sorabilir miyim acaba?
Sure.
Hocam artı 3 yazdık ama sonra nested loop'un içinde de 3 farklı operant var. O zaman n square'i de 3 ile çarpmamız gerekmez mi?
Yes, you're right, but since I only consider the power, that's why I didn't include, but you're right. And we should also have 2 here. Thank you. Okay, this is what is asked here. Any questions, guys? Since we will have a quiz at the beginning of the second lecture, so make sure that you are comfortable with the time complexities. Any other questions about, let's say, these time complexities, linear, logarithmic, quadratic, cubic? No questions? It's good, okay. Then let's jump to the time complexities of the list data structure we are using in the Python. This is a kind of a summary of the operations we perform on the list data structure in Python. As you see, some of them has constant time complexities, some has a linear time complexities, and this obviously we know that sorting is quite complicated, and they are implementing a merge sort algorithm, and that's why it is a time complexity of linear arithmetic. But other are usually linear, and some has constant in time. Since these are very simple operations, if you remember in the pop, is simply popping the topmost item, or if append is adding an item to the list, so they are a very simple operation. That's why they are independent of the size of the problem. But if you look at other operations, let's say an insertion to a specific position, since you need to find that position and do some operations, it's a bit complicated than the first 4 operations. Or having a kind of a slice, getting a slice, and k is the length of the slice, I guess. So that's why it is a different term instead of n. But we can say that it's linear in time. And here, the time complexity depends on the 2 parameters, size of the problem, and k is another parameter in the problem. So we will see such examples in our next chapters. We have dictionaries this time. We didn't discuss the dictionaries, but they are not complicated. I think you should have gone through this data structure in your tutorials. In dictionaries, we have 2 columns. It's very similar to the conventional dictionaries. You have a kind of a word and then value assigned to that given item. So it's not that complicated. As you see, most of the operations are again constant in time. But if you do some iteration or copy some portion, then they are more complicated than the simple operations. They have linear time complexities. So that's actually wraps up the time complexities or analysis of algorithms. We will start in a moment discussing the trees, 3 data structures we are using in our implementation, especially in computational geometry and computer design. Any questions, guys, before we start discussing the trees? Okay, no questions. So let's have a look at the definition. So for the tree, we need to have, as you see, a kind of a connected graph. So we need to have a connected graph first, and then we will check whether this graph has circles in it or not. So that will be the main requirement. In the trees, we shouldn't have any connected circuits, or circuits are obviously connected, so we shouldn't have any circuits inside the trees. And other thing is that tree should be still a kind of a connected graph. So we can say that tree is a kind of a subdomain of connected graphs. And as I mentioned, we will be using such data structures, and as you have already done that, we will be using these data structures to solve various problems in computer science. For instance, if you have a specific item and want to order it properly or put it into some specific folders, we may use it for compression algorithms. We will see an example about it. Or we may use it for chess. So what we do in chess, you may have many options. So from these options, you may have another option. So if you play this game, the right game, and then you may have another options, another one. So that's why you can implement an algorithm for chess problems using trees. So we have some graphs here, as you see, 4 graphs, G1, G2, G3, and G4. The question is, which of these graphs are just trees? Can anyone tell me which of these graphs are trees, or none of them maybe, or all of them? So any comments, guys?
G4, 3.
G4. One says G1 and G4. Other says G1, G2. Just G2, G4. So none of you said G3. I think G1, except G3, you say G1 and G2. So do you remember our definition? We said that it should be a connected graph first, and then it shouldn't have any circuits. So let's start from the last one. If you look at G4, this is unconnected. We don't have any connection between this part and the other region. So this is not connected. So I cannot say that this is a tree. So for tree, the first thing is that it should be a connected graph. And then the second requirement is that it shouldn't have any circuits inside. So let's have a look at the rest. I think the rest are connected, so we don't have any problem with that requirement. We should have the other requirements that they shouldn't have any circuits. So if you look at this one, I can easily draw it in such a manner. If this is C, I have A here, let's say B, D, and say I have F here, and after F, I should have E. So this is E, this is F, and this was A, B, and D. So I can say that this is a graph, right? What about the other one? This one, I don't see any circuits, but let's draw it here. So if you start with F, you may start with any roof, it doesn't matter. We have D here. This is D. And then let's have A and C. A, C. And then we have what's remaining, E remaining, right? So this is E and this is B. So I can say that this is another tree. Let's have a look at this one. It seems more complicated than the others, but I will try to draw it by using the same approach. Now I will start from D this time. We have two, let's say, children of D. One is E and the other one is A, right? And from A, I have a kind of an B, and B is also connected to B. A is connected to B, so as you see, we have a kind of an circuit here. And then what we have, A is connected to E is connected to B, E is connected to D, E is also connected to, no, that's fine. And then what we have remaining, C is remains here, so C is connected to A. I can have C here, and C is connected to F, and I think we are done. Any missing connections, guys? I think it's done. So you can see that since we have a circuit here, I cannot say that G3 is a tree. This is not valid. So we have only two trees in this given set of graphs. G1 and G2 are examples of trees. Since they satisfy the definition of the trees, they are all connected. These two are connected and they don't have any circuits inside. Any questions, guys, about the definition of trees and how we do the check whether the given graph is a tree or not? Okay. Now we will discuss some properties of trees. We'll start from basic ones and then go into some details. And the first one is about the rooted trees. Obviously, rooted is a tree. The thing is that it should have a root. And the roots will be the node actually, as you see, every edge actually should be directed away from that root. If that's the root, then we may have such children and children of other children, grandchildren. So this is the root. And as you see, every edge of this tree is actually directed away from the given root. So we have now some relations between the node numbers, leaf numbers, edge numbers. So if you have a tree having n vertices, so these are all called as vertices. We count them. And if you have n number of vertices, then that means you should have n minus 1 edges. 5, 6, 7, 8, 9, 10, 11, 12, 13 vertices. So we should have 12 edges in this tree. Another thing, if you have M-ary tree, what does M-ary means? If M is 2, then the tree is called binary. So if M is 3, then we have tri-ary trees, which means that in the tri-ary trees, we should always have 3 children. And as you know that in the binary trees, we only have 2 children, but in tri-ary trees, we always have 3 children. Let me have a binary example here, and then I'll have a look at the given property. It says that if you have such ME trees having I internal vertices, if that's the case, then it should contain this total number of vertices. So first of all, what is an internal vertex? And the ones actually at the end are called as leaves. You will see in a moment that these are the leaves of the tree. These are leaves, and the rest are called as internal vertices. So let's have a look at our definition here. Since this is an triary tree, so M is 3 multiply with I. What is the number of internal vertices we have? We have 4 internal vertices. 3 times 4 plus 1 should be equal to the total number of vertices. Is it correct? Let's check. We have 9 leaves and then 4 internal vertices. So in sum, we should have 13, right? This is correct. So it satisfies the given equation. So if the ME tree, let's say if M is 10, it will be quite complicated to draw and do some operations. Instead, we may directly use this equation. Since if it gets larger, I will not be able to sum them one by one manually. So I prefer to use such equations, such relations between the internal trees, leaves, and the summation of whole number of vertices. Any questions about these fundamentals of trees? So we have more equations, more relations between the vertices, internal vertices, and leaves. But I can say that honestly, I don't actually remember all these equations all the time. But once I need them, I find them and try to use in my implementation. So what do we have? For instance, if you have n number of vertices in your ME tree, then I was equal to the internal vertices. This is actually a different representation of the previous equation. And you may also get internal vertices by using such an expression. And we have another relation between the internal vertices, and the leaves. So they are kind of similar expressions, similar relationships represented with different equations, but they have the same meaning. We are trying to relate the number of leaves to the number of vertices and to the internal vertices. Any questions about these relationships? So we have some more properties. Another property is called the level. The level actually is determined with the help of the length of your, let's say, tree from the root to the leaf. It will give you the height of the tree or the length of your tree. And the level of your root is actually defined as 0. And then the next level is the first level. And as I said, the whole height is determined with the help of your number of levels. And this is another expression giving the relation between the leaves and the height. So another expression we have is between the height and the leaves again. So if you determine somehow the number of leaves, and if you know the size of your, let's say, tree, if it's a binary or a triary, then by using this scaling logarithm function, we can determine the height of your tree.